So the field aperture telescopes have traditionally been used only one sensor at the focus, or even when you use a phase array with a large number of elements sampling the wavefront incident on it, and the sensed output is combined. Typically, people have been combining that to form only one output. So it's an equivalent of a single pixel camera. And you can imagine how difficult it will be or painstaking it will be to scan a picture with one pixel at a time. So you have to devise some ways of scanning across the area, in this particular case, the area of the sky, while you can look at only a small piece of it at a time. So imaging by raster scanning was a routine thing. It's also helped by the Earth rotation, where you stay put at one declination or something, and at that declination, the entire right ascension range becomes accessible over the 24 hours, and then you can change the declination next day and do the same. And this is how you can row-wise sample a matrix and put the information together. So these are the telescopes that I was showing you. One of the, starting from the left top. Now I have an advantage of the cursor with me. So this is the Grotreber backyard telescope that he built to go to higher frequencies. This is the RRI millimeter wave telescope, which doesn't exist anymore. This is the all familiar GMRT dish. This is the Jodrell Bank telescope, Lowell telescope. This is the Green Bank telescope, which is 110 meter diameter. This is the Arecibo telescope, which got damaged, unfortunately, recently. This is the Uti telescope, which is ingeniously built on a slope of a hill with the slope matching with the rotation axis of the Earth, so that one-dimensional movement can track a source. This is the Gaurividnu telescope, which I have played with a lot, which is a 1.5 kilometer long array, which has a huge collecting area, works at 35 megahertz, very long wavelength. This is the Mauritius telescope, which was set up to study the center of our galaxy and the part of the galactic plane from Mauritius, which is a joint collaboration of IAA, RRI, and Mauritius University. This is an array of antennas example. This is the MWA tile, which is also something that we are using as a phase zero antenna for the SWAN initiative. So essentially, you'll find that you have focus either as a point in all these cases or as a line in the case of the Uti telescope. And here there's a virtual focus where the signal sensed by different pieces of it, elements, are combined together by hand. Here, the optics takes care of combining them at the focus. This is the biggest single aperture, fast, which has come about in the recent times. It's a 500 meter diameter, but this is not steerable. People have advanced sense, as I said. You have many pixels now. There are the 144 pixel cameras are now made at radio. This is a picture of the 7 beams, what used to be an alpha instrument on the Arecibo telescope, where you can make measurements in 7 directions simultaneously. Similar feats exist at Parkes telescope with 13 pixels and so on. This particular one has probably 49. So people have advanced in various ways, but you can also get multiple pointings by a technique that we're going to describe later, where you have array of dishes and elements on the ground, and you combine the information from them in a way to produce ability to look at various directions simultaneously and distinguish them from each other. But in doing all this, the signal that we pick up to our antenna element is so weak that it needs boosting by many orders of magnitude. And you would find that powers, even with decent bandwidth, would be typically of the order of minus 110 or 120 dBm. Now, to get it to a reasonably recordable level, at least a few millivolts sort of voltages, you would require these to be amplified by typically 100 decibels. In doing so, you will have to pay a price. Whatever device you use might add its own noise because it's at finite temperature. There is random fluctuations occurring in the equipment itself, and that can be sum totaled and represented by an equivalent temperature associated with that noise power as T receiver. What you require is also coherent amplification, in the sense you do not want to change the information that you have received, mix any aspect or information at one frequency with another frequency in the band, because we would like to study them separately. So you need coherent amplification, where it's in olden days they used to have audio amplifiers which were called high fidelity amplifiers. What it meant is at each frequency you have only a scale factor describing this amplification. So you might have a scale factor which might depend on frequency, and the input and output are related by this simple factor. So as I said, we desire amplification, and the price we pay in terms of additional noise that we add in addition to what we have from the antenna. So the typical receiver chain looks like this. You have some kind of transducer which gets the signals translated into electrical signals. You have initial amplification, which you pay a lot of money or efforts to ensure that it does not produce large amount of noise. So these are called low noise amplifiers. Then you select the band of interest that you have by putting appropriate filter. These are analogous to the filters you use in optical, where you choose the color appropriately. But in this particular case, it will be electrical circuits with inductors and capacitors and resistors, which will affect selection of the band of interest. When you have the signal coming through, for convenience of choosing any subsection of the spectrum and not having to change all the other equipment based on that selection, you can effect conversion of frequency, where you have something in the spectral band that you want to look at. You can always translate that information into a convenient fixed frequency. In this particular case, for example, 150 megahertz is that chosen frequency to which you translate any information coming at a selected band to 150. And so if it's coming at 1420, you choose a local oscillator or local tone, where you multiply this information with a sinusoid. And you can see that if this signal itself is thought of as a combination of sinusoids at different frequencies, each one of them will multiply with this sinusoidal function. When two sinusoids multiply, you know that from your trigonometry that you can write that as sum of two sinusoids, one at a frequency which is sum of these two frequencies that you multiply, and difference in the two frequencies. So you can arrange either the sum or difference to be the frequency that you want. So by choosing the appropriate local oscillator, you can, which is in this particular case different by an amount that you want finally as an output, you can pick a particular band. And so this is called the RF, this is called the local oscillator, and this is called the intermediate frequency. The intermediate frequencies are chosen so that you can have the rest of the operation of the receiver at a fixed frequency. It's also useful in a very important way, that when you amplify these signals by 100 dB or so, even a small leakage here of the signal would radiate, in terms of radiation leakage from any one of these components, would travel to your antenna and get picked up, and that will be way stronger than what is being received from the sky. And this way you might actually have local feedback, and the feedback based on the sign of the feedback can result in either oscillation or saturation of the signal at this location. To avoid all this, what you do is, while this frequency was allowed in, the translated frequency, which is at, let's say, a different one, this is not allowed through the main gate of the system. And so you can happily amplify these signals without worrying too much about radiative leakages in the process of amplification. All right, then you select the band, and then you can have even another translation for other conveniences that you might have. And then typically these days people convert the analog signal into a digital form, and which can be recorded onto computers, and then you can do further analysis and so on and so forth. So this is the typical receiver system or the electronics that is associated. You don't have to remember any gory details about it. The only thing to really remember is you should know how much amplification is required. You want it to be coherent amplification. That means it should really represent what was at the input. It should have utmost similarity with what the input, except the amplitude. We have already touched upon this aspect. Maximum power transfer requires impedance matching in any circuit, and this is not just limited to electrical circuits. Even when we have the feed and looking down on the reflector, you have to worry about maximum power transfer, and you have to match the characteristics of the feed to the reflector, so that power is not wasted and it's really radiated on reflection in the correct direction. Impedance matching is also important while I'm actually talking to you. Unless we are really coupled well, whatever I'm saying might just get lost. So impedance matching is a very broad concept for maximum power transfer. What happens if you do not match? There will be reflections. There will be, not everything will get absorbed in the way you had desired. And the reflections, in the cases of signals, will interfere with the forward going signals, and you will find that it leads to interference between the two, or superposition of two will decide how the net signal will vary, and that you will find leads to patterns which are called standing wave patterns. They will exist both across the space dimension as well as in the spectral dimension, because after all, the interference depends on the relative phase differences, and the phase differences will depend on the wavelength and the spatial dimension. You will find the prices will be paid in terms of loss of signal and efficiency of your setup in general. You will find it can happen even in the way you might do software analysis using certain software. If it's not matched to the kind of characteristics of the signal while you're trying to detect a certain pattern or certain attributes of the signal, if the improper mismatched filtering that will happen effectively will lead to you losing the ability to detect that particular aspect for which you're doing the analysis. So please keep this in mind. The optimum way to get a result out of something is to match, pay a lot of attention to the matching aspect of what you're looking for and how you are looking for it. We already answered this question. The only part I want to highlight here, which I've written in different color, is the coherent amplification also implies there is linearity in the system. By linearity, one means that when I change the input by a certain factor, I should see exactly same factor increase in the output. The association of, so that my measurements of the output can easily relate to how things were at the input, and any changes I see at the output are easily attributable to a genuine increase in the input rather than something else. So those require a lot of care in designing the receivers. It's not easy, and there are people who are masters of designing such things. What happens in linear systems is if you can send an impulse, a delta function input to the system and ask how the system will respond. And these are typically used as descriptors of the behavior of the system, and they're typically known by this name, impulse responses. You will find for a linear system, all the inputs, if we were to imagine them as made of a set of delta functions with different heights coming at different times, which is very acceptable description of the input. We can choose this delta functions as finely in time as you want. Each one of them gives rise to the characteristics that are described by impulse responses, which are scaled by the height of the delta function at the input, and the timing reference to the when the delta function is given as an input. The output can be described as a superposition of impulse responses corresponding to each one of the impulses at the input. When that description holds good, this is what is required for linear system. You will find that the output is a simple convolution of the impulse response with the input pattern. And this is something that you can use profitably to understand how the system will behave to a certain input. And as I said, whenever you're trying to detect something, you will have to ensure that you're doing any choosing or any analysis operation which is amounting to selecting things, which is, generally you can call filtering. You have to look for the pattern optimally so that your output, which says yes, you have found it, is really representative of the fact that you exactly found the pattern you're looking for. So it's another way of saying it is, suppose you want to find out whether this key is similar to the one that you have. One easy way is to design a lock or take the lock that your already available key opens and see the new key is able to open that or not. And so the filter, the way you detect the desired is by designing a conjugate filter. When you want to see, so the conjugate here is the lock, and you want to look for the same key, and so you design a filter or a selection criteria which is based on the lock, which is a conjugate filter. And this is something that you will encounter in all aspects of detection, regardless of whether it's astronomy or elsewhere. And it turns out, in the presence of Gaussian noise, random noise, match filtering is the best detection technique. We can now ask how sensitive our receiver or the system is, how faint an object we can detect. And that depends on the number of photons that we have collected in the bucket that we have per piece of information that we will record independently. And independent piece of information is available to us at the rate given by the bandwidth. That means if our bandwidth is so many hertz, we have independent piece of information coming at intervals of inverse of the bandwidth. We can use this advantage that we have independent pieces of information coming at individual intervals. We have seen that individual pieces of information have required information in terms of the mean value, but it also fluctuates by an amount which, thanks to the exponential distribution, we know that the fluctuation is 100%. The mean and RMS, the mean is our desired parameter, but it can fluctuate by an amount, which is the standard deviation typically. And that itself is equal to the mean. That means we have 100% uncertainty in each one of the measurements that we make at intervals of inverse of the bandwidth. How do we get to the estimate of the mean that we want to have? And this is where the uncorrelatedness or independentness of individual measurements coming at intervals of 1 upon the bandwidth will actually help. It's like asking large number of people. Each one of them might give you an erroneous answer or a correct answer, but added with the same truth, but different amount of lie. If you ask large number of people, you need to take an average of what they have said, you will distill out the truth. And this is exactly what we do. We know that each one of the pieces of information has the mean value and some deviation from it. And the deviation is random. The deviation in one sample is not related to what the next sample looks like or any time later. And so we can treat all these as independent measurements and combine them. And when we do that, you will find the number of such samples can be described as the time bandwidth product. Simply that per unit time, we have number of samples which are equal to the bandwidth, and the amount of time over which we collect this information will give you the time bandwidth product. So the number n, the number of independent samples you average, is simply described by the time bandwidth product. You can see that these days, even with large amount of noise in the receivers and in the even in the sky background, you are able to make detections at sub millijansky level, where the Jansky unit is as described earlier. So you can rely on using large bandwidths and long integrations to make more and more sensitive measurements. This is in addition to collecting large number of photons by using large collecting areas. So the radiometer equation, as it's called, which describes the sensitivity of a telescope, is formally can be written like this. We will work in temperature units, but you can also use some other units if you wish. So this is essentially the equivalence of intensity or power. I'm trying to get my cursor down. Yeah. So the RMS fluctuation that you would see, against which you will be assessing any presence of the signal that you might be looking for, it has to be few times the RMS for it to be not considered a chance fluctuation of the random variations that you will generally see. And this is calculated by, accounting for efficiencies, if any, that you need to account for. You will have system temperature, which describes the total amount of noise fluctuation, noise power that you have in the system, which includes what you get from the antenna and what you add as a part of the receiver. As you said, this is the amount of noise that you have, and for each sample independent piece of measurement, which is done over a duration which is inverse of the bandwidth, you will have 100% fluctuation. So you will find the fluctuation will also be of the same magnitude as the mean that you are looking for, which is the thesis. And so the time bandwidth product, square root of it, will decide the way the fluctuation will reduce when you integrate or add together large number of such independent pieces of information, each coming at the interval of inverse of bandwidth. So if you integrate for a time t, you would have got delta nu times t int as the number of samples. You could also add additional factor of number of polarization measurements that you have done, which if you want to add them together, NP can be 1 or 2 based on whether you made independent orthogonal polarization measurements. So this number is the number of independent samples you have averaged together. You got an advantage of reduction in the RMS by an amount which is 1 upon the square root of the number of independent samples. And this is the essence of the technique to make your radiometer or measurements sensitive. There is no other way of than having increased area and so on. So the antenna temperature, as we have seen, is the measure of the power that we have actually received, and then we try to equate that to a fictitious situation where we say, if I have a resistor and if it has to produce the same power that I have received from my antenna setup, what should be the equivalent temperature of this such a resistor? And this is something that you are going to look at in one of your worksheets, so I'm not going to dwell on this pretty much. A source which covers the entire view, we can argue from simple arguments that it's as if we are sitting in a heat bath. It will appear like we are sitting in a heat bath, and the antenna temperature will be same as the source temperature in such a case when it's fully covered. If it is covering only part of our view, then you will find that you will have to do the averaging, and so a bright temperature spot of smaller angular size, its contribution will get diluted effectively when you try to find an average temperature across the peak. This is what can also be used to quickly estimate the antenna temperature when you are looking at a source. The antenna response, although we would like to have directivity, which very ideal, where we look at certain sector, we want to assume that it's not looking at any other part of the sky. You will find that this is not true. While we look at some direction sector prominently, we are also looking at with a little bit of response in other directions, which are called side lobes. When you want to look at any one source, of interest. You are not guaranteed that that's the only source in the field of view that you have. You might have other sources also present, statistically speaking, based on the solid angle that you're looking at and how the sources are distributed in the sky, and which sources you can detect, which sources you can not detect discretely, is based on your sensitivity and the resolution together. And when the resolution is poor, you suffer from additional uncertainty due to what is called confusion. It depends on how they are distributed in intensity. That means you will find, if you look at what is called log n, log s relation, this is the relation of the number of sources with certain flux density or flux density greater than certain limit. You will find that it's a power law, and you will find large number of sources with smaller intensity in the sky. Although they might be the ones that you want to study at given resolution, they might be a nuisance when you want to study a particular source or estimate its intensity. You have to also take into account what other sources were there in the field, because you cannot tell them apart, but you can estimate statistically what might be the typical contribution they might be making. So your sensitivity not only depends on the formal thesis divided by square root of time bandwidth product, that kind of expression. It also depends on how clean your measurement is, what are the other sources of confusion that you might have. Yeah, so we have bandwidths of two kinds. The information content where the fluctuations are in time, and there is also bandwidth in terms of spatial frequencies, and that is measured in units of distances divided in units of lambda. And this is relating to the aperture domain. And this is what we will find, that there is a Fourier relationship between that spectral domain and the angular domain, which is what we're going to exploit. So, but we have seen in terms of resolution, the limiting angular resolution is related to the inverse of the span in the spatial domain. The lambda by d expression is basically a reflection of that. The spatial frequencies also depend on the temporal frequencies because of the common thing of lambda here.